are forming in different parts of the atmosphere. And I guess, once again, this is the sort of thing that starts exciting me, is that what it's saying is that dynamical information inside the stars, which are being picked out by the fact that these waves are propagating out through the stars as they're doing these pulsations. And so different species respond in different ways. Here's barium 2, and this gets a bit ugly here, but what you can look at is this is silicon 2, has a little dip here compared with the standard one. Silicon 1 looks pretty flat. This is calcium 1, which looks pretty flat. Calcium 2 is all over the place. And so what's happening is those calcium 2 lines are forming well out in the atmosphere compared to things here which are forming deeper in the atmosphere. So you're getting information, you're getting three-dimensional information out of the spectroscopy. So this has gone a bit further than just plotting up a spectrum. You're actually interpreting this in terms of velocity information, how the star's moving. And it gets really quite complicated, and Michael did some lovely stuff here and I'm not even going to talk too much about this, but basically what you have to do is understand how moving atmospheres produce these little black lines. Alright? This is the sun, produces these little black lines. What happens when you have a moving atmosphere, you have different parts of the atmosphere can be producing different parts of that spectral line that we actually observe. And you have to dig back down and try and understand that in terms of the dynamics of the atmosphere. Alright, so that was just looking at single Cepheids, and then Orland did his PhD with Michael and I, because Michael had come back as an academic at that point. And he was looking at binary Cepheids, and they're interesting because you have a Cepheid pulsating with a partner which is a main sequence star. So Cepheid's a big star, a supergiant. Its partner is a dwarf star, still burning hydrogen in its core, whereas the Cepheid has gone off and started doing double shell burning, or whatever it's doing. So, Orland did a whole lot of these things. This is an interesting set of diagrams because you can see, it's actually not very good to see this, but this is 48,000, this is in Julian date, this is 52,000. We didn't drive him for too many years, but we've been collecting this data for a little while. And then what we had, we were able to put all this stuff together and then look at the long-term variation of these things and get out the orbital parameters of these things, because we know the pulsation of S Musk is about a 10-day Cepheid, but it has an orbital period of about 500 days. And so that's a bit over a year and a half. In a PhD in 4 years or 3.5 years, you're not going to get many cycles there, so you do need to go back in time. But Orland was then able to put all these things together and understand. Oops, you better go to the right one. And one too many. And then be able to work out what the ratio, because you now have orbital parameters, you can now work out what the ratio of the mass of the Cepheid to the companion, and you can therefore deduce various things about how it's going on and actually understand what the mass of the Cepheid is, which then becomes important. If I go back a couple of slides to this one, it's important in terms of testing stellar evolution, because what you can do is you can actually put the two stars in the binary onto an evolutionary track for a 3, a 4, or 5 solar mass stars, and realise that if you look at the ratio there, so it's about 15% different. The Cepheid for S Musk has already got up to here. S Musk B, the main sequence star, is sitting over here on the main sequence. They're not much. This was 5.4 to 5.0. You can see that just 0.4 of a solar mass can get you well away into a different phase of evolution. And that's sort of being able then to test those things using the orbital, the dynamical information about the stars not about the two stars, not just the dynamical information about the Cepheid itself. That has all sorts of implications if you think a little bit about it in terms of how some people then use Cepheids in terms of the distance scale and whether they actually understand how the lines in the Cepheids they're observing in some very, very distant galaxy are actually formed. Yeah, as I said, I then got back into globular cluster work after a 30-year break with a couple of people. I guess it was Liz Wiley and then Claire Worley and then later on Jeffrey Simpson. So there's sort of the sequence in here. And basically, some of the questions that were still back there where there were these stars which had strong CN and weak CN bands and anti-correlations with the G-band. So this is our friend the G-band again. Not weak G-band stars, but stars which have different strengths of the G-band and different strengths of this cyanogen molecule as well. And I think if I do this right, oops, there's very, very subtle things here. Some of you in the front will be able to see there's a difference between these two stars here, the squiggles here, and this is the sodium line. So there's differences in the sodium abundance in these stars which have different amounts of cyanogen. And it's one of those things which then becomes it, and it doesn't occur in other things. Here's some of those S-process things that we were interested in. More S-process here, zirconium, barium, they all look identical. The carbon, the calcium, and there is a sodium line in here, but it's very well varied. This one's better defined out here. But it's just a way of trying to understand how some of the nuclear processes that occur in these stars, in the different sorts of stars. Now, what's become apparent in the globular cluster sequence is that there's lots of different sorts of globular clusters, and we could do a whole talk about globular clusters, and I'm not planning on doing that tonight. But the key thing is to be able to understand how these globs of maybe 1 million or so stars have evolved, and some of them have come from different. Omega Cen in particular has come from possibly being stripped out. It was probably a dwarf spheroidal galaxy that's essentially been stripped of most of its stars and been left with the things that we see today. And there are remnants from that which people are now trying to look for. And we have a paper that's coming out. Well, it's gone to the referee. Hopefully it will come out in the next 6 months about that from the project that I'm working on at the moment. But it's now we understand there are lots of different groups and subgroupings of these stars. I'm just going to say there's a sodium CN correlation. So when you increase sodium abundance, the strength of the CN lines goes up. So there are correlations that you can see. So these are stars in here. These stars, in terms of their temperature, their surface temperature and their surface gravity, are essentially identical, but they have, when you have strong sodium, you have strong CN. So there's processing that's occurring here, and nucleosynthetic processes, which are part of this story that they're trying to tell us. And this is sort of trying to show, now, I guess most of the stuff I've shown you here has been what we call high resolution, high resolving, spectral resolving power. So we're able to see the individual lines. What we were interested in, and this is stuff with Jeffrey Simpson, was to go looking for data that was of less high resolving power, spectral resolving power. And this was a group of 1,600 stars, so you can see from 35 or so to 1,600, starting to do a lot more stars, but you have to compromise. The compromise is you can't do as many stars at high resolving power because it takes much more telescope time. So you've got to compromise. But we have our favourite regions, and you know my favourite region down here, which is the CN and CH region, and there's the calcium, not singing line, there's a neutral calcium line that sits in there as well, and there's a barium feature that is buried in here. And so Jeffrey collected this data. I mean, it was archived data. You could just go and get it off wherever you could find it. And this was from the AAT in Australia, but some other people have used it for completely different reasons. And he worked out where all these stars were. Now, what am I going to do? Colourmagnitude diagram. Well, it's basically, this is luminosity. This is how intrinsically bright it is. So these are the brighter things up here. This is a colour. So these are red here. These are blue stars over here. And these are all giant stars. And now these are all stars in a cluster. We know these are cluster members, but you can see they're spread across here. And in fact, if you look carefully, you can see some sequences. There's a sequence through here, there's a sequence through here, there's probably even a sequence through here. And they are different groups of stars which have subtly different properties and sometimes some grossly different properties. In Omega Cen, there are some stars which have the overall metallicity which is only down compared to the Sun by maybe 20, and there are other stars in it which are down by a factor of 200. So it's a huge range of metallicity within this one cluster. And it's one of those things about Omega Cen which is very bizarre. It's been thought to be anomalous, but it actually turns out there are other clusters that have similar, more subtle, but similar sorts of sequences that you can see. So what Jeffrey did was to play some games where what he did was he matched the spectra. He just said he computed synthetic spectra, and then he matched those synthetic spectra to the observed spectra and got out an index. And he got out some things which is an overall metallicity, a carbon abundance, a nitrogen abundance, and a barium abundance. And we stole the sodium and the oxygen from the people who'd done some of the studies before. And what he was able to do with much lower spectral resolution was to actually start realising that where all these sequences, I don't want you to try and understand it, but this is the sodium against oxygen, nitrogen against carbon, and the different symbols are these different populations of stars which were on those different sequences. And not only do they have different overall metallicity, but they live in different areas in this plane and in that plane. So that you can start doing some clever stuff, much too clever for me, but k-means clustering, which is one of these statistical tools that you can do. There's lots of statistics you can do on these things. And you can work out how many groups you think there might be and how you can parameterize them with all these metallicity parameters. Okay. Yep, that's it. Many of you know about Hercules, so I guess I played with Hercules in my youth, in 2003-ish, I guess, maybe 2005. That's Stuart Barnes, who some of you might know. And of course, this was, one of the late Graham Kershaw's, greatest mechanical engineering things that he did. And so these were some Delta Scuti stars that we observed spectroscopically. So it just looks like there's some fuzzy lines here, but those fuzzy lines are telling you that there's been some Doppler shifting. There's been shifting of those lines with respect to the observer, and so therefore there's been some velocity shifts. So I mean, this is stuff that Karen Pollard does now at Canterbury, does a lot of work on that, but we had a few students who were working on that. This was a master's project a long time ago. And then there was SALT. Not going to say much about SALT. I said something to Phil earlier about it, Phil Jock. But SALT, Southern African Large Telescope, maybe that was a long time, I don't know. So it's an 11-metre telescope in South Africa that the University of Canterbury was part of from the beginnings. It then is now not part of it, so that was on the stamp series back a few years ago. And this was the spectrograph that the team at Canterbury, so Stuart did a lot of the optical design with Michael and with Damien Jones from Prime Optics in Australia, and Graham did a lot of the, did all the mechanical design for it. So this was a two-beam spectrograph. So I had a red and a blue camera, which got all the spectrum. All right, go back to this. You got all those colours in 2 CCD. and it was designed by us. We got it through an incredible process of design reviews, internationally refereed design reviews, which was pretty harrowing for us, but we got it through in 2005. And it was eventually built by Durham. By then there was some funding issues within the SALT consortium. They didn't have enough money to build it at that point, and basically our team started disintegrating. I mean, Stuart left, he was doing a PhD. Some other things happened that we really couldn't bid for it, and it was built, and it's working now in South Africa. Right. I have a galah. I am an Australian, as you may or may not have noticed. And we got one of these when we went to a conference about galah, and I'll tell you what galah is, but I retired in 2013 from my academic position at Canterbury. I did an interesting thing, which I was talking to Tim and Sergey about. I ran a private college, international college for undergraduate students for 3 years. That was something completely different. I'm not going to talk about that. But then I reconnected. I sort of stayed connected with galah. It started in about 2012-ish. And what it is, galah stands for, there's acronyms in astronomy, Galactic Archaeology with Hermes. Okay. So, it's actually about the things that Beatrice Tinsley was talking about, which was about how galaxies evolved. Now, we want to look at our galaxy. And remember we were talking about if there's any biological sciences people here who do things with n, statistical things with n. You know, I started off with 1 or 2, we got to 30 odd, we thought we were doing well. You know, with Jeffrey we were doing 1,600 to 2,000 stars. Our goal is to do 1 million, and we've done pretty well. We've done about 650,000 stars already. So that's getting spectra of these things. That's a lot of spectra. It's a lot of things to analyse, but there are some really clever techniques that you can use these days. So, we can do 400 of them simultaneously in a field, so you're getting 400 spectra. So that's pretty good multiplexing. So you've got 400 stars that you've done, and so you can do about, I don't know how many, 10 or 12 of these fields a night. They take about 1 hour each, and the clever thing is, the way I'll go forward and then come back. Hopefully we'll go forward. It says going forward to the, oh, it's a terrible picture, to the AAT, but this is the Anglo-Australian Telescope. It's still called the Anglo-Australian Telescope, even though the Anglos are no longer there. So the mirror is down here, the 4-metre mirror is down there. This is the interesting bit up here. What it has is a robot up there, and the robot is a fibre positioner, which can position those 400 fibres in about 45 minutes. Now you may say, well, you're wasting 45 minutes while you're positioning them. But no, there are 2 plates. So while you're observing for 1 hour on the other plate, you're positioning the fibres on the other plate with the robot up the top end of the telescope. And the robot is not you or I or anybody else. It is a robot, and it is an amazing thing to just watch it do it. It just does it. And you just go on to the next field, you just slew to the next field, and you observe for the next 400 stars. So it's a great thing to do. And I mean, the reason we want 1 million stars is we want to beat down our statistics. We really do not want to be doing, you know, n is equal to 10. We want to be n is equal to 1 million, because then you can really start answering questions about the stars, the composition of the stars, because we get their surface temperature and gravity. We know how to do that pretty well, but we can get the abundances up to 30 elements. And the way this was done was with Hermes, and Hermes was a spectrograph which was explicitly designed for this particular project. So it has a blue and a green and a red and a yellowish camera to do 4 pass bands of about 100 angstrom, about 10 or 12 nanometers each. Not very much, but if you pick those pass bands, which is exactly what was done for this thing, it took a couple of years to work out which particular pass bands, but we picked the pass bands to get the elements that we were interested in, the significant nucleosynthetic elements that we were interested in getting. And so you get these things for 650,000 stars. You analyse in detail a training set, and you probably know where I'm going here if I talk about training sets, some of you people who work in various fields. You do about 12, 15,000 stars which you analyse in detail, and the rest of them you do machine learning on. You just have a thing which then looks at the squiggles on this thing and says which squiggles in your training set, which squiggles does this correspond to, and you can actually interpolate within these things to get abundances to an incredible precision. Amazing precision. And the team are doing all sorts of amazing things. I mean, I'm part of it, but I'm not involved in some of those things. But it's an amazing to see when you put a group of about 100 scientists together that you can actually extract these things. And then you can come up with nice, pretty pictures like this, which you may say, it's probably just good to look at the numbers here. So this is the number of dwarfs that we have. I mean, it's different for different elements. So this is carbon, oxygen, sodium, magnesium, aluminium, just a few of the elements, between dwarfs and giants, and 250,000 dwarfs, 120,000 giants, for which we have what we say are good parameters. And this is just, if you look at the colour bits, this is sort of the density map of where our stars are. The lines here are from a separate survey that was done in the north, completely different and a much smaller sample. And for the dwarfs, once again, some things in the north from a much smaller sample. So this was from our data release 2, which was from just last year, 2018. But a cast of many, as I said, about 100 of us or so that are involved in it. So really amazing stuff that you can start doing to now start understanding things about how the different elements are built up in different stars. And to just talk a little bit about that, one of the things that we've done is that we want to look, because we have 650,000 stars, and you then go looking for needles in haystacks. You go looking for stars which have some of the properties, for example, of the things in Omega Centauri. And what you can do there is you can find things in velocity space as well. So you know that if a star used to belong to Omega Centauri but has now been kicked out somewhere, it'll be in that sort of velocity space. So Jeffrey Simpson and a group of people in Oz have been doing that and have found a few stars which are nowhere close to Omega Centauri, but appear to be part of that, being kicked out of that cluster. So that's one of the things that we're trying to do, is to connect together objects that are no longer in the same part of the sky. So that's probably about all I want to say. We've done a whole lots of things. I do all sorts of other things as well. Since I'm retired, I can do anything. Commissioning art, doing things with a thing called the Children's University, and keeping myself generally occupied. But thanks, and I hope you haven't all fallen asleep.
Thanks very much, Peter. It was a very fascinating talk. I did not realise just how much information could be extracted from stellar spectra. So it was very,
I can't turn the lights up, so that's how much I know.
We can go some of these up.
Oh, there you go. No, you have to press them harder, that's all.
So we'll have a few questions. I guess the one I had first was just occurred to me at the end there. You're talking about identifying stars that might belong to the Omega Centauri cluster. Is it possible, I know there's been speculation about the Sun and whether its siblings can be discovered. Will that method work for that?
Yeah, I mean, one of the things to do is to look for stars, and it's not just with Omega Centauri is a bit weird in lots of ways. But what you want to do is look for solar twins, but look for stars that may have been absolutely identical in these abundances to the Sun. And in some sense, a lot of that will be in other clusters, like what we call open clusters, so clusters which aren't as dense. And many open clusters, not dense like globular clusters, will actually dissipate in a relatively short time. And so they can be skewed across the whole Milky Way, like we see across this room. And then what you want to be able to do is use the signatures of all the abundances of those elements to find ones which are identical and find one. And that, I can tell you that the bottom line is they're bloody hard to find. And you know, we found a few, but not as many as we thought we would find. So yeah, there's lots of things at different levels as we process this information. What we find is there's very many subtleties in the modelling side of things that you do have to understand. And I'm not going to go on, but there's things about, we call it thermodynamic equilibrium. We use that as our way of understanding that the atoms have come to thermal equilibrium. But if they haven't come to thermal equilibrium in the atmosphere, then you can get all sorts of weird and wonderful things. And you have to understand the atoms. So you have to understand a lot of atomic physics to understand what's actually going on. So it's actually, it really builds on things like that. So finding needles in haystack is quite tricky.
A couple of questions.
Oh,
just one, sir.
just one. Okay. The very short one. For Hermes, which code do they use now to synthesize spectra?
Which are they using? Actually, I'm not sure what
Is it
they're using.
Well,
They're using a thing called SME, Spectroscopy Made Easy, as the first cut of it. And then there's a lot more detailed stuff that people are doing with the people in Karim Lind is working on some non-LTE, non-thermodynamic equilibrium codes. And they are all definitely, Caru's was definitely an LTE code. Yeah. Yep.
All right. With some of the parameters here, I make it F and lambda, and there's even some terminology looking a bit like phase-like loop. I'm wondering if there's a periodic table, and there's a base 9, because you've got, there's a F, E9, and then 92, is it uranium? Is it like a base 9 system, and is each element basically its own phase-like loop?
Oh, you mean in terms of the periodic table?
Yeah.
Well, the periodic table was done by the gentleman, Lynette, very good, back in 1869, and those elements in that periodic table were such that, he says, trying to go back in time here, I know I can go back, let's go back to the periodic table, because it is quite good to start at the very beginning and understand it. But if you look at, going back to that one, I mean, they were put in those elements because of the electrons in their outer layer. So these were, and it all gets built up that way. These are the inert gases. Yeah. So it's weird base. And then these elements here are things that fit in over here. They're the actinides and lanthanides, and it's all a bit. It is very very weird, but it's all to do with atomic structure that I have forgotten apart because I haven't done it since 19. But that's to do with the atomic and nuclear structure and how the different elements are built up.
Would they be locking into its own?
Well, the electrons are in orbits, and as you fill orbits, you fill different shells. That becomes chemistry, and I sort of get scared away. Yep.
You know how you scan 400 stars an hour, right?
Yep.
Because it's light part of the day, how many do you get to actually do in a day?
Well, you only do it at night.
Yeah, but how many hours? So if you get 400 an hour, how many hours do you get to?
You get in the winter you get a good 10 or 12 hours you can observe. In the summer you can only observe for 6 or 7 hours. So in the summer you only get, say, 6 fours, maybe 3,000 stars. In the winter you get 10, 12,000 stars.
So you're only observing each star once? Or?
We only observe, generally we only observe each star once. We go back and do some particular fields again just to check that we're getting the same parameters, but we tend to want to get to 1 million stars, so we don't want to keep observing lots of stars. So it's not like people who want to do and look at one star and see what's happening, maybe it's pulsating or whatever. Yeah.
It would take about a year to get all of them?
No, it'll take us about 5 years to do it.
Why 5 years?
Because we can only do about, we don't get a certain amount of time on the telescope. We don't get the telescope for every night of the year, so we don't get 365 nights a year.
Yeah.
We get a reasonable number. We probably get about 100 nights a year at the moment, maybe 80 to 100 nights a year.
Yeah.
So, yeah.
What's the clear sky percentage like there? It must be fairly good.
It's a bit better than the land of a long white cloud, but sometimes not as good as you hope.
If you're say your Spectroscopist survey was strong enough,
yeah.
I mean, you're looking for stars with extremely low mechanism?
No, we're looking at any star. We look at every star. That's globular.
The survey will find stars with extremely low.
It will find some of them. It's not going to find them as well as some other people looking photometrically have been looking for them. Because the thing SkyMapper here in Australia, which is photometric, has been trying to identify, Mike Bessel and his gang, have been trying to do it, and that's why I don't run down photometry. But you can work out where those ones will be. What we wanted to do was not be selective about it. We wanted to observe just the whole thing. I mean, we don't go too close to the plane of the galaxy, but we also don't go a long way away from the plane of the galaxy. And the reason is, if we go too far away, we only get 100 stars per field, and that doesn't actually utilise 2D. So we actually are, our selection criteria is pretty good. We understand, we just observe everything.
You wouldn't expect to find the extremely low mechanism stars in this.
No, that's true. It's probably in the halo. We do have some fields. We're doing some stuff with TESS and Kepler. We've done some of those overlap fields to do some follow-up with them. So, because it's sort of nice for them to be able to get the astroseismology parameters to tie them in with 20 or 30 abundances of the elements as well.
Any more questions before we finish? We have supper down the far end. I guess it can't be clear outside, or Andrew would be inside telling us the augmentation.
Oh yes.
No, that's all right. It's still 5 minutes away. And if anyone can hang around a bit afterwards to help clean up, would be appreciated as well. So thanks again, Peter. And before we go, I'd like to make a presentation on behalf of the society.
Should I open it up or will it explode?
We have a spectroscope, must be liquid.
I did actually bring a spectroscope.
Oh my God.
It's a pair of binoculars. That's very impressive. We have a monocular at home, which is actually quite nice. I have because sometimes I find it's easier. But this is very beautiful. Thank you very much. Thank you. But I do have a little. Actually, I do. Where did I put it? Some of you may have remembered me from many years ago. When maybe you guys gave it to me. Did you give me a little old handheld spectroscope? But there's a nice little spectroscope here, and if you want to, it has. I mean, a spectroscope really just has a slit and a dispersing element and an eyepiece. I mean, that's all it is. It's a very simple thing, and you can either use a prism as a dispersing element, or you can use, which I didn't do, which my other trick, or a piece of diffraction grating. You can. I mean, nowadays we tend not to use prisms. Some people do, but if you look in here. Quickly, looking in here, you'll see the colours of the rainbow. I mean, I'm happy to, but if you look up, you look at the lights, look at any light around here, you'll see the colours of the rainbow. Obviously a bit tricky to see the dark lines, but you should be able to see lots of emission. Yeah, it's a bit hard to see. You can focus it, you can move it in that. It may have been Cass that gave me that. They must have found something. Yeah, when I gave the talk there.
Too good to give away.
I know stealing it. But yeah, it is a fun thing. As you can see, I've been doing it. My long-suffering wife is here. She's had to listen to this. Well, only this 50 minutes, but of course I've got excited about spectroscopy since I guess I was, when did I start? 1974, I guess I started my PhD. And Deidre used to bring the cat and night lunch up to me at the telescope when I was working at Mount Stromlo on the now defunct 74 inch, which is no longer there, got burnt in the fire. And the 50 inch, in fact, the old Melbourne telescope, which then ended up as a 50 inch telescope on Mount Stromlo, and then ended up as a microlensing telescope, part of Muncher. So, yeah. All right, no, go eat meat, eat, drink, and be merry, and I'll be there, so you can